Okay, in this video, we're just going to reiterate the important parts of work and what the work energy theorem is. So work, symbol capital W, units are joules. It's work and energy are basically, as I think I've said before, like the two sides of the same coin. Work changes the energy of an object or a system, and energy is the capacity to do work. So they like get interchanged back and forth. Doing work can increase or decrease the energy of a system or an object. And if you have energy, then you can kind of put that into work and make something like speed up or slow down. Essentially, work is force times distance. Forces do work or changes the energy of an object or a system. We really always, every time you're looking at work being done, ask, it's done by what on what? So forces are doing the work, so you ask the work done by what force in particular, or if you're looking at the net or total work, then that you'd be talking about the work done by the net force. So the work done by what force? What particular force, or is it the net force? On what? On what system or object is what the work is being done on? What system or what object are we talking about? Work changes the energy of an object or system. Positive work increases energy, usually speeding it up. Negative work decreases the energy, usually slowing it down. And net work means total work. For just like net force was the same thing as the total amount of force. You added it all up. And net work is going to be simply the work done by the net force. So if you already know what the net force is acting on an object or system, then you can use the net force to calculate the net work. If you only know some of the forces that are acting on the object and not all of them, then you're not going to be able to determine the net or total work. You need to know all the other work being done by other forces. Lastly, the work energy theorem states that the net work always equals the change in kinetic energy, W net equals delta K. I have an object here. Let's say there are a bunch of forces acting on it. Let's say gravity pulls down, normal force would push up. But let's assume we've got a frictionless surface here. Frictionless surface, and I'm going to use a similar example to what I used in class for most of the classes. Let's say I have a force applied up here at an angle. We'll call it FA for applied force, and we'll draw our other forces in because our free body diagrams are still very useful for getting a complete picture of everything. There's FG. Normal force is going to be less than FG because I have a little bit of an upward force from the upward component of the applied force. We said frictionless, so there's no friction. That'll be pointing to the right. I'm sorry, pointing to the left. As I think these are all the forces I want to put on here. So if this is the result, then I'm going to have an unbalanced force to the right from the applied force. And we'll say that the block is going to move horizontally to the right. And it'll start from virtually no speed. So it's speeding up pretty much from rest. We'll be fine. That's an A. Hold on. Delta X is what I'm trying to write here. This is our displacement to the right. Come on. Erase. So in blue I have my displacement to the right. And it's frictionless, so those are all the forces acting on it. I need to label this angle here because this is the angle that's going to separate my displacement vector from the applied force. And the applied force is the only one that is not perpendicular to delta x. So when we define work specifically, and as you've already read in the notes undoubtedly, that the work is equal to essentially force times distance, but when we get particular, we would say exactly how much force we're talking about, or how much work rather we're talking about. It's force multiplied by the displacement multiplied by the cosine of the angle in between those two vectors. So FA is the applied force. If I'm looking for the work done by this applied force, then I have FA the force, I have delta x, the distance over which it's applied, and then orange is theta. And that's the angle between those two vectors. Okay, and that's That's because only a portion of that force Fa points in the direction of the object's motion. Only the portion of Fa that points in the direction of the object's motion actually does work. So there's my red line here indicating the portion of the applied force, Fax, that's in the direction of the object's motion. The other portion of Fa is vertical and is pointing in the opposite direction of the gravitational force, called Fay. And Fay is not doing any work. The object is moving horizontally to the right, so only the forces that have parallel components, or components that are also horizontal to the right, or also horizontal at all, are going to do any work. If they're pointing to the right, then they're going to do positive work and help the thing speed up. If there are any forces that have horizontal components that are pointing to the left, then they would be pointing in the opposite direction of the object's motion and be doing negative work and taking energy away from it, trying to slow it down. So our work here, if we said work by what? The applied force, then we would have force times delta x, the distance over which it's applied, times the cosine of the angle. And that angle is theta. If we asked what's the work done by the normal force, then I would have Fn, that's my force, times, well, delta x, okay, times cosine theta. Well, what is the angle theta between the blue delta x displacement vector and the normal force? It's this whole thing right here is 90 degrees. So what's the cosine of 90 degrees? Yeah, 0, right. So the work done by the normal force is 0 because it's perpendicular to the object's displacement. And I hope you can see from the gravitational force, the work done by gravity would be Fg times Fn times, no, not Fn, what am I talking about? Fg, the force, times delta x, times the cosine of, you could say negative 90 degrees, or if I went all the way around, that's going to be how many degrees? 270 degrees, which means the cosine of 270 degrees is also 0. So the work done by gravity is also going to be 0. The gravitational force is there, but because the object is not moving vertically at all, the gravitational force does no work. So the only thing that does work is this red component, the horizontal or x component of the applied force, Fax. That's the total amount of force in the direction of the object's motion, and that's the amount of force that's going to determine the work done on this object. So there's the work that's actually getting done, Fa times delta x times cosine theta. Now, if we said this thing had an initial velocity of 0, which is what I said at the beginning, and we said, what is its final velocity going to be? Question mark. We can determine this by the work energy theorem, which states that the net work, the total work done on an object or system, is equivalent to the change in kinetic energy. Now, velocity is related to my kinetic energy. So if I'm ever looking for, like, what's the final velocity or what was the initial velocity, I probably want to consider some point in time where the object has kinetic energy. All right, so if we do an LOL diagram for this guy and see if I can figure out with my knowledge of work and energy and the work energy theorem what the final velocity is. That should round us out for this video. KUGUS, I'm doing my LOL diagram. I need to label what points in time. So I'm just going to say initial time and final time. I'm going to call it TI. T final. Initial time is going to be when this thing is at rest. At TI, its initial velocity is 0. And at some final time, it's not 0. It's being accelerated. Specifically, it's being accelerated by the applied force, Fa. Even more specifically, it's really just this component of the applied force that's making it speed up. And that's going to do positive work, increase the energy of this object. And therefore, at some later point in time at position delta, after we've gone displacement delta x, and the block is at this position, it'll have some final velocity. That's what we want to find out, and that'll be at t final. The objects in the system are block is what I've been calling it. There's no spring, and there's no gravitational potential energy that we're mapping out here. We're saying it has zero gravitational potential energy because it's not changing height. So whatever its position is now, we'd call the zero vertical position. Okay, so it's just a block. Let us see. Initially, kinetic energy, do we have any? No, because we're saying it starts from rest. Its initial velocity is 0 at time initial. Does it have any gravitational potential? No. It's not changing height, so we don't have any change in gravitational potential anyway, and so we would just call wherever it is right now the 0 line. There's no spring in there, so it's got nothing, right? There's nothing. Final. It has moving energy. Let's give it 3 blocks. UG is still 0, US is still 0. Okay, so what has happened here? First you can ask, is mechanical energy conserved? Does initial energy equal final energy? Question mark? No, because we don't have the same number of blocks in each L. So energy was added to the system. So I need to draw an arrow in. So that energy was added to the system. How much energy? Well, we have this change in kinetic energy that's going to be equivalent to the net work done on the system. So this is equivalent to the net work that was done on our system. What did work on the system? Well, all the forces that were acting on the block or on the system. We had normal force, that did 0 work. We had gravitational force, that did 0 work. We have this applied force that did an amount of work equivalent to FA times delta x times cosine theta, or an amount of work equivalent to the red force in the x direction multiplied by the displacement delta x. That was the total amount of work, or the net work, that was done on the system. So we can write down here, well, we know that net work is going to be equal to FA delta x cosine theta. Because that force is at an angle, I got to have that cosine theta in there. You can think about it as you just need the portion of the force that's in the direction of the object's motion. All right, so now I've found the net work. So my initial energy was 0. I got an arrow, right? So here's initial mechanical energy is 0. And then my final mechanical energy, I have 1/2 m v final squared. Because my final energy is all the kinetic energy. So I'm just saying, let's calculate the kinetic energy. 1/2 m v final squared. All right, so initial energy 0. Final energy is all the final kinetic energy. And we gained energy. We had energy added to the system. How much? Well, it must be equivalent to the net work. So I can write out a mathematical statement now. I can say initial energy, what I started with, which was nothing, plus the net work, which is equivalent to the change in energy from the work energy theorem, is going to be equal to, I get my plus net work because I got an arrow going into my system. Initial energy plus net work is equal to final energy. Initial energy is 0, so that's 0, plus net work is FA times delta x times cosine theta, is final energy, which is the final kinetic, which is 1/2 m v final squared times delta x times cosine theta equals 1/2 m v final squared. And then if we said, okay, well, what's the final velocity? Can we solve something for that? Yeah, I've got twice FA times delta x times cosine theta divided by m is v final squared. Oh, gotta take the square root. There we go. That's how fast the block is moving after it has traveled that distance delta x. It's the square root of twice the applied force times that distance times the cosine of the angle between the applied force and that displacement vector divided by the mass of that block. So we've just used we've used a bunch of stuff here. We've used free body diagrams to think about the forces acting on the block. We've taken our new understanding of work and the definition of work mathematically to show exactly what the work is done by each force. 0 by normal force, 0 by gravitational force, not 0 by the applied force Fa. We keep in mind that the applied force Fa, well, the only amount of work it actually does on the object is the amount of work that is related to the amount of force in the direction of the object's motion, which is the red portion of the force. We take that stuff, we say, all right, let's look at an LOL diagram, because now Mr. Stacy's asking me to figure out what's the thing's final velocity after it travels the distance of delta x. So you set up an initial time with our left L, final time over there. Look, we gained some blocks. Increased energy. Positive work was done. Arrow must be going into the system. There it is. Arrow going into the system, net work. We have a change in energy. What's the net work acting on the system? That's going to be energy added to it. Well, this chi, because that's where we got it, right up there. That's the total amount of work being done on our system. And then we can set up an equation that's saying, right, our initial energy plus net work done on my system is going to be equal to our final amount of energy. And that'll show we gained a certain amount of energy. And then we wanted to find VF, so we just solved for that at that point. All right, so here's one example of applying the work energy theorem. And this is just a block being dragged horizontally. So this is not one in which you have multiple objects or a lot of things happening. In reference to the lab that we did, or are about to do, depending on what class you're in, if we have our car that starts up here and it goes down the ramp and picks up speed and slides into the garage, which is right here, and then the garage and car together travel some distance delta x before coming to rest. And as I say in the lab, imagine that everything's frictionless, nothing matters until you get to this point. From this section, there is friction between the garage and the surface of the table. Then what we have is all gravitational potential energy up here. Over here, we've got all kinetic energy. And over here, we could say our final energy, perhaps, if you'd like, is 0. And so energy changed. From the work energy theorem, we're saying W net is change in kinetic energy. Here we got kinetic energy. Here we have 0 energy. So our kinetic energy is gone. What did that work? Well, kind of like our block over there. In my previous example, I've got normal force acting on my car. I have Fg, and I've got this kinetic friction after the car's in the garage and sliding across the table. So as you can see, the net force is the kinetic frictional force. That's going to be the net force. So the net work is going to be the work done by friction. And that work done by friction must also be equivalent to the change in kinetic energy. But our kinetic energy must be equal to the original amount of gravitational potential energy we had up here by conservation of mechanical energy. So really we could write Ug is equal to K is equal to the work done by friction. And this is going to be Ug, let's say, initially, K when it reaches the end of the track, which I'll call T for the track, K at the track, and then W, work done by friction, removes all that energy from the system. All that energy is dissipated. And so when you go into the lab and you practice this, you say, if Mr. Stacey wants me to find a value for the work done by friction, some amount of joules, well, the work done by friction is going to be equivalent to the kinetic energy it had at the bottom of the ramp, or also equivalent to the amount of gravitational potential energy it started with. So you calculate whichever one of those you want to find. And then the second part of that lab was, or will be, depending on who you are, is finding the coefficient of kinetic friction, which you should be able to do that because we already studied forces. All right, that's all for work and an example for work energy theorem. We'll have another example of work energy theorem stuff because it's applied a lot and makes a lot of problems a lot easier to solve. All right, that's it. Bye.